All right, let's do dynamics in NTB coordinates. Now, a reminder of the kinematics. The velocity in NTB coordinates is purely in the tangent direction. There is zero normal component. The acceleration has two components. It has v squared over rho in the inwards normal direction and dv dt, or v dot, in the tangent direction. Now, rho is the radius of curvature. It's simply r for the circle. But if we have a different function, say y equals x squared, then you would calculate the radius of curvature using this relationship here, as previously derived. Let's do a few simple problems in NTB coordinates. So the simplest one, the pendulum swing. So here we have a pendulum swinging back and forth, and it moves in a circular path. We want to find the tension at the bottom of the swing, or the bottom of the path. So at that point, its velocity will be tangential, and our coordinate system is going to have n hat in the inwards direction and then t hat in the tangent direction. And we think about the forces on the mass, the 5 kilogram mass. Obviously, there'll be weight downwards towards the center of the earth, and then there'll be tension in the cord. Now, because there is an inwards normal acceleration, the tension must exceed the weight. So we sum forces in the normal, or n hat direction. We have tension in the positive n hat direction and gravity in the negative n hat direction. Now the sum of the forces must equal the mass times the normal acceleration, and the normal acceleration is v squared over rho. The tensions are what we're looking for. Rho is, in this case, going to be the radius of the circle, which is just the length of the string, which is 4.2 meters. So we can solve that for the tension. And we get 59.76 or 59.8 newtons. So there's the first and simplest problem in NTB dynamics. We would have done problems like this in Physics 12. Next, here's another Physics 12 problem. We have a car driving just in a circle. Now we're looking at the car from above, and the car, let's just assume without loss of generality that it's moving up the page, so that defines the tangent direction, tangent to the circle, and then of course we have the normal inwards direction. Now in terms of the forces acting on the car, obviously the car has weight. That weight force will be going away from us, so there's an arrow going away from us, and then the road will be pushing up on the car that's coming towards us. Here's an arrow coming towards us, and those two forces just cancel each other out. In order to go around the corner, there must be inwards friction acting on the car. That comes from the tires on the road. So we again, let's fix that, there we go. We again sum forces in the normal inwards direction. There's only friction. That must equal the mass times the normal acceleration, which is v squared over rho. We're again moving in a circle, so rho is just the circle radius. Now, we will also use two facts. We will use the fact that friction is mu Fn, and we will also use the fact that the normal force and the weight are balanced in this case. So, how does that help us? Well, friction is mu times the normal force, and the normal force is the weight, so we can substitute here mu times the weight. That must equal mass times v squared over r. Mass of the car cancels, cross multiply the r. That's v squared, so v is the root of that. So we can substitute in the given values, which are 0.75 and 50, to calculate the speed. So 0.75 times 9.81 times 50 meter radius, that's v squared. Take the square root, 19.18 meters per second. This is another Physics 12 level circular motion problem. Let's try one that takes us a little bit beyond Physics 12. It's the same car driving around a circle, but now in this next example, the car is actually going to begin at rest, and it's going to accelerate and pick up speed from rest. So we're still going to have the same coordinate system, t hat, the tangent of the circle, and then n hat, the inwards direction. In this case, though, the force diagram is a little bit more interesting because we still have inwards friction, which is going to keep us moving in a circle. It's going to change our direction. But the force that accelerates the car, well, the engine spins the tires push back on the road. If there's friction, then the road will push ahead on the tires and therefore the car. So the force that actually moves the car forwards is also friction. So we see F, force of friction. T is for the tangent component. F, N is for the normal component of friction. So those are two components of friction. There's actually two components here. And if we wanted to, we could, draw the resultant friction. The resultant friction is kind of going to be the vector sum. It's going to be the vector sum of those two, and it's kind of going to point in that direction. I'm not going to draw it on there. Okay, so as I said here, editorial comment, there's an inwards component, which turns you in a circle, and a tangent component that allows you to pick up speed. So, if we sum forces in the normal or n hat direction, we've got the force of friction normal, which equals mv squared over rho. That's the normal acceleration. Now, our mass is known, our radius of curvature is known. What is true about our speed? Well, in this case, we're picking up speed at 1.25 meters per second squared. So we know A is dv dt, dv is a dt. At our initial time of 0, our initial speed is 0. This is a time integral. This is a velocity integral. Our acceleration, though, is just a constant value. So the integral is very straightforward. On the left-hand side, the integral dv is v. Putting in the limits, you get v minus 0. And then on the right-hand side, you just get 1.25 t. So, because the acceleration is constant, we're really writing here vf is vi plus a times t, but we're approaching it in a more sophisticated way. So there's an expression for speed as a function of time. So the normal force, the normal component of friction also varies with time. It's m v squared over r. All right, let's next sum forces in the tangent direction. Well, it's the tangent component of friction. That must equal the mass times the tangent acceleration. What is the tangent acceleration? Well, it's dv dt. And we know that dv dt is our acceleration. It's a constant 1.25 meters per second squared. So our tangent component of friction with 1200 for the mass times 1.25 is actually a constant value. It's 1500 newtons of force. Now, what are we asked to actually find in this case? Well, we're told that the car speeds up from rest and eventually it begins to slip. Now, it will do that when friction has reached its maximum possible value. What is the maximum possible value? Well, friction is the maximum possible static coefficient times the normal force. See, static friction is a variable from 0 up to a maximum. In this case, I'll just got to scroll up and see the number, we're told the maximum coefficient of friction is 0.75. Now, we know the normal force is 1200 G. What friction is this, do you think? Is it the tangent? Is it the normal? It's actually neither of those. It's resultant. This is the resultant. It's the hypotenuse. So it will slip when the normal squared component plus tangent squared component, that's the resultant friction. When that reaches its maximum value, which is 0.7 times Fn, which is the same as the weight. Okay, now let's get an expression for this. This was 1500 squared, and this was 0.7. It was 0.7, not 0.75. Sorry, scrolling, death scrolling. No, it was 0.75. Should have stuck with my intuition. 0.75 times 1200 times G, 9.81. So for the normal component squared, if you simplify the above, it's 37.5 t squared. That's 1200 over 50 times 1.25 squared. And then that's all squared. So we see when we expand this side, or rather calculate the side, 0.75 times 1200 times 9.81, that's 88.29. And then we'll square 37.5, 1406, not a quarter, but just 1406, t to the fourth, plus 1500 squared, all in the square root, is 88.29. So we'll take 88.29, square it, that gets rid of the root, subtract 1500 squared, that's 1406 t to the fourth, so we divide by 1406, that's t to the fourth, that's t squared, and that's t, 15.2 seconds. So it's at 15.2 seconds from the point of departure that this car will start to slip. So you could calculate the speed if you wanted using this, and you could calculate the distance using another integral. So those are 3 problems in NTB dynamics. This last one's a little bit more complicated because it also included the tangential equation. But that's a quick look at the dynamics in that coordinate system, and we'll do some more problems in class.